Please go ahead.
Perfect. Thank you, Xuyang, for the warm introduction. Um, so today I wanted to give a overview about the uh, some recent work in my group on reduced order modelings for complex dynamic system in terms of both control and for the idea of data-driven control and surrogate modeling for PDE. So it's kind of a summary of the work that my group my group has done over the past 2 years. Okay, so okay. So first, I wanted to. So the plan for today, I wanted to, quickly, have, state out the, clearly define, some of the challenges that we have nowadays, and still in the in the design of aerospace systems, and as a goal, and naturally, what is the goal of the research that we're doing, and also some of the modeling philosophy. So there's still a increasing demand for designing more and more complicated aerospace systems, and the traditional simulation-based design for such system facing you are currently facing unprecedented expensive simulations. So if you think about this, for even for on the left, you see it's a real world combustion systems, where in each of these combustors is actually a dozens to hundred of these little injectors that's circulating around the perimeter. Okay, so let's say on the right, you see it's kind of much more simplified version of it. It's There are only 7 injectors, but as you can see, uh, there is a need to analyzing the interactions between those 7 injectors, and even just seven those injectors would take weeks to simulate because of the stiffness introduced by the chemical reaction, and you have to simulate the system over a long time or period because you wanted to capture something actually much more slower than the chemical reaction, which is combustion instability, which is actually determined by the geometry. So there's a lot of complicated things going on here, but the major problem is the stiffness, introduced, which is introducing the computational inefficiency. Okay, so we need faster yet accurate enough modeling frameworks for better design, and also for many other things like optimal control, uncertainty quantification, sparse sensing, data assimilation, which leads to perhaps a little bit more popular concept in recent years like predictive maintenance and digital twins. Okay, so the key observation here is answer to the most of the problem, can be easier if you are reducing the complexity of the system, in terms of that when the system is lower dimensional, but it's still nonlinear, then a lot of those problems can be computationally tractable. And that's where most of the applied mathematicians are play their games. They come up with some fancy algorithms and apply it to Lawrence 96 problems, or maybe just Lawrence systems. But there's a lot of interesting can be play over there. And most of the things, in terms of um, tractability, it's okay. Or if you make those assumptions further more aggressively, saying that, can I actually tackle instead of tackle the full high dimensional nonlinear system, can I instead tackle something lower dimensional but also linear system? Then some of the problem above can actually have closed form solutions. So one example is, for the optimal control problem, if your objective function um, is just linear quadratic, you can solve the um, uh, Ricardi equations, discrete Ricardi equations to find the closed form solution for this basically the LQR. Okay. So here is the modeling philosophy here. That's what I believe. There are currently 3 modeling philosophies right now in our world. The first one is the forwarder model, where you simulate the full system, And this is traditional path of numerical simulations. We try to write the most efficient parallel algorithm, and we are running on the biggest machine that we can find on the Earth. And we also looking for the most complicated problems. And our entire hope is we hope the Moore's law still holds. And the ideal situation is in 2080, we can, perhaps arrive the, if Moore's law still holds in 2080s, we can arrive, a full scale um, uh, full scale high reference number direct numerical simulation, which is really high fidelity, but perhaps not for this combustion. Okay, so there's another, because of there's so much computational cost in the first paradigm. The second paradigm decides to instead of tackling the forward model, can we actually project the high dimensional um, system into a much lower dimensional? You can either project into a linear one, which is what I'm showing in the figure here, or you can come up with some fancy uh, nonlinear manifold to project. Recently there are some popular works in quadratic manifolds, which usually from applied math. Um, Side of the community, and from the engineering side of the community, most people tried. Romit has also done a lot of work on this, using deep learning framework like convolutional autoencoders. Okay, so in any case, the idea is to lower the system dimensions so that we can so so that at least when we are propagating in time, we don't have this big N as big N meaning perhaps a million degrees of freedom in our computational cost analysis. Okay, so the final one, which 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 is uh which is kind of being a little bit further aggressive, is to assume that perhaps we can replace the nonlinear dynamic system with a linear one. Okay, but if you can do that, then you not only you have very analytical closed form formulation to forward propagate in time, but you also have a lot of ways to explain the high dimensional system. So it brings explainability into the modeling framework. You know, um, so there are many other related works. Things like Koopman operator is one I'm going to talk about today. There are also things like depends on how you think about depends on how you where you find the linearity. You can also uh, just try to find try to extract the linear operator within a nonlinear high dimensional system, and you try to analyze the resolvent of that linear operator, and that becomes the popular analysis in turbulent uh, turbulent flow community about the work Beverly McKeon, who was previously at Caltech, currently at Stanford, working on the idea of resolvent operator, looking at all the spectrum and forcing and response modes. Okay, right. So there are some trade-off. I'm not saying that any one of the framework is superior than the other, or any one of the framework is inferior to the other two. So there are always some trade-offs. In the first category of the modeling philosophy, it is most accurate. Well, there's some condition over there, but it is definitely most expensive, and it doesn't require any data. For the second, paradigm of family in the middle, let's say for the reduced order nonlinear, models, it's moderately accurate. That's empirical, moderately accurate. It yet preserves the physics from governing equations, and it requires some data. It requires some data because if we wanted to get to the lower dimensional manifold, um, or getting these mapping from lower dimensional to the higher dimensional, we need some sort of decoder. So that decoder actually is learned from data, either through SVD, POD, or through some recent work is also using SPOD from Aaron Town, or just using a deep learning framework to have this lower dimensional to a higher dimensional mapping. Okay. And the third one, it's arguably, the least accurate. But it can, because of linearity and low dimensional properties, it can usually, deployed in real time. But usually it requires a lot of data, because it doesn't preserve any physics compared to the previous two. Okay. So the rest of the talk, I'm going to talk about a data-driven, linearization with the Koopman operator, which falls into the third category, and the and the and the and this and this and another second topic I want to talk about is surrogate modeling of time-dependent PDE, which is kind of falling to the second, between the second and third ones. Um, okay. So the first topic I'm going to talk about is data-driven linearization of Koopman operator. So let's go back to our system analysis courses. And given a nonlinear dynamical system, let's say this is a discrete, dynamical system. What we one of the most important things that at least I learned from nonlinear dynamic system courses is to analyze those system behaviors by, if there is a hyperbolic equilibrium point, you can we know that you can the Hartman-Grumman theorem tells us we can always find we can always just do linearizations by using first order Taylor expansion uh, to um, to find an equivalent linear system around that hyperbolic equilibrium point, and that would be conjugated to a linear system. So that's something really nice, because when we have the linear matrix, we can analyze in the eigenvalues. We know everything. We know everything. We know the behavior of the at least asymptotic behaviors of the nonlinear system near those equilibrium point. Okay. But the problem is, with those linearization is, I know this linearization is really powerful. And if you go to control literatures, a lot of the modern control, when they're dealing with nonlinear systems, they start with this approximation. Either they start with exactly what I said here, um, you know, uh, or they start with the perturbation around the reference trajectory. And if you go there and look at how they find, analyzing the perturbation around the trajectory, that's again, it's still Taylor series expansions up to the first order. Okay, so however, the problem with those approaches is that it doesn't really provides an accurate, single linear system across the entire global phase space. We know that these linear approximation will fail once we go out of the some region, the vicinity of this equilibrium point. To be honest, we don't have really a good idea about when should we accept the approximation and when should not. Okay, so instead of figuring out the exact boundary, can we actually find a global linear system that could has the hope to conjugate it to the nonlinear system? Okay, so here there is a very important idea introduced um, in 1931 by Koopman, and later on being brought up by Igor Mizik, and Igor had done a lot of work, especially you know um, paving the ways for the theoretical foundations for Koopman operator and its variants under different situations, either for stochastic random systems or for non-autonomous systems. So the idea of Koopman operator, because I feels like from Xuyang's interaction with Xuyang, I feels like most of you have a rough idea about what is going on. So mathematically, Koopman operator is basically it's an operator that mappings functions to functions. So the observable here is just a fancy name for functions. It just means this function is defined on the state space of the nonlinear dynamical system. So let's say this function called g for any of such functions. Koopman operator is nothing but just a composition operator with the observable and the flow map. So the flow map is just a oracle, tells you the given a initial condition, it tells you the where these state are going to involve after delta t. Okay, so um, all you need to do is just do a simple composition. And as you can see from the equation 3 here, you can easily convince yourself that this Koopman operator K, subscript delta t, is a linear operator. If you, let's say, if you have linear combination of those functions, and you will find out that um, the action of the Koopman operator can be a linear combination of those actions of the Koopman operator on those each individual little observable G. Okay, so under some conditions, Koopman operator can admit a spectral decomposition. These conditions usually I'm not trying to elaborate anything here because those conditions actually changes. It changes depending on a lot of conditions. And I don't think, as an engineer, I feel that's too much into the weeds. But in general, we believe that uh, the under some conditions, the Koopman operator admits a spectral decomposition which can decompose this contribution of this action, and action of into three parts. The first part is the time average, the overall long time average of these observables. The second part is the point spectra, usually refers to the point spectra, which the basically means that we can project the observable into some linear combination of what's so-called the eigenfunctions of this Koopman operator. And they will be associated with a eigenvalues, which is the one you see here, e to the power of I times 2 pi times omega j times delta t. And the third part is the continuous spectra, which corresponds to the usually corresponds to the chaotic nature of the flow. So that means, instead of having discrete, discrete countable eigenfunctions, you're going to have actually it's a projection measure, the epsilon, theta over there, and there will be it is not necessarily a continuous version of the eigenfunction, but maybe just if you first time see it, you can regard that, but this is not rigorous the way of to think about this. Okay. So, however, in this lecture, I'm not going to talk about anything about related to continuous spectra because it is not really relevant for the engineering purpose. Because in engineering, we want something lower dimensional, which is definitely finite dimensional. So we will only keep basically the first two. Okay, so that is our assumptions here. So here again, it's a big if the continuous spectrum part can be ignored. We effectively have a lower dimensional, Koopman invariant subspace that is spanned by those eigenfunctions. And once the nice thing about those eigenfunctions is that when the Koopman operator acting on those eigenfunctions, it is going to be just a linear multiplication. It is a scalar multiplication between eigenvalues and the eigenfunctions. Okay. So now, if the system state X is lying on such subspace, then the eigenfunctions form the natural basis for global linearization of such nonlinear dynamical system. So this is a really nice property. For engineers, this is the final punchline that that's the reason why we want a Koopman operator. Okay, to introduce in this community. So let me give you an example here. This is a 2D 2 degrees of freedom nonlinear dynamic system. The nonlinearity comes from the second component where we have the x1 square over there. So here, if you choose a some kind of nonlinearity actually coming from the equation, because we saw x1 square, why don't we just choose a nonlinear coordinate transform by saying that phi1, phi2 is still the same as the x1, x2, but the phi3 has some nonlinearity in the equation here. And then through the chain rule, we can find out that the system becomes in the new coordinate system becomes a linear system. So this is really you can verify by yourself. This is a really good example to illustrating why under some situations nonlinear systems can be fully linearized and globally without any Taylor expansion approximation. Okay. And finally, this 3 by 3 matrix here is called the finite dimensional representation of the Koopman operator. Okay, on this particular actually three-dimensional on this particular three-dimensional subspace spanned by phi1, phi2, phi3. Okay. So as you can see here, the goal is the challenging things here is to given a nonlinear dynamic system, how are you going to find out this nonlinear coordinate transform? So that is the game here. Okay. So there are some practical questions we need to ask. So first one is how to choose such a nonlinear transformation phi if you know the governing equation. And actually later on, I will show you some examples that when you don't know the governing equation, what you're going to do with this. And the second one is how to choose, how to ensure that we have noise robustness, because sometimes in the real life there's always some noise, and for any machine learning algorithms, one has to consider the robustness to noise, okay, and how to ensure that we really find the Koopman algorithm functions. And the third part is how to adaptively sample training data given some specific task. So this is actually is a question to general machine learning, not really just restricted to Koopman operator. Okay. So the goal for today, for the first part, I will try to answer all of the above practical issues. So the first one is answer to the Q1 here is given a nonlinear system with input, we adopt the idea of the polyflows from Jungers and Tabata in 2019, or equivalently in the Colab subspace method from Mesic in 2022. The idea is to consider time delay embedding in more of an analytical form, more than just more than just in the pure measurement sense. So given if we have the right hand side of the equations, and we can construct such a time delayed embedding by using the governing equation that we have. It's just the composition of the system without the actuation. Okay, so as you can see, this vector valued observable Tn is constructed with the non-governing equation, and later on, when we don't know the equation, we actually replacing this f with a neural network, but we still keep the same, compositional structure. Okay, so now from a practical viewpoint, the practical viewpoint is actually heavily biased model predictive control. We're looking for a system with the following constraints and formulations. So we're looking for a nonlinear. We're looking for a lower dimensional system hidden state Z, and the subscript for Z just representing the time step here. And we're hoping that the latent state would follow a purely linear actuated input output system. So the learnable things here is the matrix A, which is a transition matrix, and the actuation matrix is B. It's referring to how the input is going to change the hidden state. And finally, how do we getting from the hidden state to the original system state? We use a system matrix C here. So the system matrix C here, so it doesn't really need to learn because the first part of the embedding is the system state. Okay, so here's some disclaimer here. This is not the most rigorous form, but the most favorable in monotonic control, because because of the part for the B, we didn't consider anything bilinear. And even even bilinear, it requires some control affine assumptions. So this is definitely not the most rigorous form, but it's kind of control oriented from a control oriented perspective. Okay. And by the way, if you choose bilinear form, then the entire multiple control will not be convex. So there's some trade-off you have to play here. Okay, so the answer for to the Q2 is how do we actually, the Q2, just quick reminder of the Q2 is, it's trying to how to ensure noise robustness and how to ensure we really find the Koopman function. So we're not really biased by some polluted algorithm functions and algorithm values. So we're leveraging the idea, from mostly actually from the uh, actually it originated, I think, from the natural language processing community, recurrent neural network. Later on, I think a lot of and this entire SIML community realized this is really powerful tool. Okay, so this is not something totally new here, but just using the recurrent loss over a simple one-step loss here. So, and we find out this algorithm is actually way much better than all the other fancy regularization algorithms. If you consider that, just if you want highest robustness out to the noise. So here, this rollover loss is basically formulated as given a sequence that you sampled from the system, which you have the initial condition and a sequence of control input. Correspondingly, the nonlinear system will have a corresponding response, which is in the system state space. Uh, and then you're going to minimize the difference between the predicted trajectory, which is come from the previous equation, follows the previous three equations, with the ground truth response of the actual nonlinear system. And as you can see, this problem is definitely very challenging. It's a challenging offline optimization problem. Okay, and where the thing here, the A and B are the matrix to be determined. Okay, and the the UIJ here denotes the input at i's timestamp of the J trajectory. Okay, so note that this trade-off is to deal with a non-convex optimization rather than a convex optimization in offline sense. So there's some trade-off here. So there's also a few other tricks that we tried to use this to improve the performance. So we avoid the issue of stacking a poor local minimum by using the curriculum learning ideas. So interestingly, these curriculum learning ideas is kind of hidden everywhere in everyone's papers, especially in the apatics. We don't really find anyone seriously talking about this, but in this year, I think in ICLR 2025, 2024, last year, I think, yeah, it's last year in Europe's, there is paper on APE bench, and I think Felix also talked about these issues. Interestingly, you somehow we're still relying on some heavy engineering dirty tricks to make things work. So the idea of curriculum learning basically instead of having a really huge rollout to train in the beginning, which will fail miserably, you started to roll out gradually and use the previously optimized A and B as the starting point for the next rollout. So, and second thing is we adopt some stabilized formulation for Koopman operator so that we can ensure, the Koopman operator is definitely going to be stable. This is also, this is actually appears from my paper in 2020, and some other variants has also come out by using Lyapunov functions. So this is definitely not the only way, but just one way that we choose. Okay, so the answer to Q3 here is, I remind the Q3 is, how do we adaptively sampling training data given a specific task? So So the answer, to Q3 here is, Koopman operator is learning from data. So how would one actually sample high-dimensional data? Well, if you think about that, in a naive sense, it's not really much we can do, except just, having some hypercubic design of experiments, vanilla design of experiments to fill the high-dimensional space, which is not working very well. But if you think about that, the task that we're doing, if we have a goal, let's say we have a task for control, then perhaps we can come up with something smarter. So this is something we come up with my student Sharia. That we iteratively collect response of the true system under control input, synthesized with the previous data-driven model. So then we use the new data to update the data-driven model, and this process can be, repeated several times. So this is the overall framework that we come up with. But I want, to highlight here is the iterative part, which is, you start with, let me see, I can have a pointer somewhere. Okay, so you start with, these trajectories and you collect some data, you throw into our framework, you generate a reduced model, and then you do some control interact with the actual system. And then actual system might fail. Some of trajectories actually, turns out to be a failure. Then you go back to collect the true response and the corresponding control input. Go back to augment into our training trajectory data. The rationale behind this is that if the model made a mistake, that means the corresponding response trajectory must be new to this model. And if that must be new to this model, condition on the model is well trained, it must be new to this model, then we augment. And that's be new to this model, and it's important at the current stage. It's something important. So we augment into the training data and then training with this augmented data. And it turns out it's actually very effective. If we wanted to quickly have some impression of this. So this is the impression that we have here. So if you have the data augmentation, you can stabilize the system way much better if you don't. And we find out usually you just need start augmenting 2 rounds. That's usually enough. And even just augmenting with 1 round, you can quickly see some significant improvements in the downstream control task. Okay. All right, let me go back here. So we did some, just sanity check, starting with the simplest example ever possible. With our, toy example, the variable oscillator. So we first did, a I hope this is the most comprehensive, benchmark against, all the other noise robust, Koopman algorithms out there. It turns out that using this trick here, it's already eliminating the forward backward DMD or totally square DMD, which are pretty famous in the literature. As you can see, our algorithm has the lowest noise level, which is the brown one, and we once we have some confidence on the prediction part, which is just the forward part, the control part, which was the carpool problem, and we also find out the prediction. This is sorry, this is not prediction. This is the MPC cost, which is once you have the model, when you do you formulate a predictive control problem, and you're trying to measure the control performance by just measuring this difference between desired trajectory. And the predicted trajectory and the corresponding how much energy did you put into the system to control it. Okay, so it turns out it's way much better than a standard extended DMD with the radial basis function, which is supposed to be the standard to-go algorithm. Okay. And we have seen the effect of iterative learning. It really helps a lot. Okay, so we actually also do the further verification. Xia, how much time do I have?
Usually I can go to 15 minutes more maybe.
15 minutes more? Okay, got it. So I need to speed up. So we have some further verification with mountain car problem. the left is prediction, the right is MPC. As you can see, our dissipative, our either the standard rollout or the dissipative rollout is outperforming the other two, the standard DMD and the extended DMD here. And we also tried the problem Luna landing and the Panda Reacher problem. Okay, so I'm not gonna talk too much here. Okay, so in summary, to summarize, eigen function of the Koopman pair offers a way for global linearization of nonlinear systems, and which can be useful for faster MPCs. And we provide several best practice on how to learn Koopman operator under noisy environment with known equations. And we demonstrate the proposed framework can work on canonical nonlinear system prediction and also MPC problems. Okay, so is there any quick question I can take for now? Okay, so now I'm gonna uh, go to the third part, which is the surrogate modeling for time-dependent PDE. So for surrogate for the time-dependent PDE here, so here the problem that we're interested in is a parametric time-dependent PDE. So imagine the parameter is the Reynolds number and the equation is Navier-Stokes equation. Of course, when you're changing the Reynolds number and the viscosity, the behavior of the system will significantly change. Okay, so the interesting thing here that the problem that we're talking right now is given the initial condition, given the parameter that how you're going to predict how the system evolve, and we will compare our given a large amount of data, and we will compare against the ground truth solution coming from a traditional numerical solver. So there are a list of ideas, can do this. The one we talk about today is, the reducer model here. So you can either do an intrusive reducer model, or you can do a non-intrusive one. So the non-intrusive one is what we are looking at today. This is the reason why I said this paper is actually between the second paradigm and the third paradigm, because we're not necessarily enforcing the physics here. Okay. So inside of the non-intrusive realm, we have we adopting the idea of autoregressive modeling of the latent space dynamics. So this is you can say some of the ideas like LSTM with CNN also falls into this category. So this is our model basically falls here. Okay, so the overarching idea that we using for the mapping from lower dimensional to higher dimensional is using something called implicit neuron representations. So implicit neuron representations is basically the idea of using the coordinate as the coordinate of the PDE, let's say XYZ, as the input to a neural network. And then the output is the quantity of interest that we, at the point of XYZ. And as you can see, if the parameter of this neural network changes, the corresponding field will change. So this process of affecting the parameter is called modulating. So this is basically this is the overall idea that we basically I'm quickly going to show you that we use a linear latent space and a linear quadratic latent space to modulating these networks so that we can do some predictions in the PDE space. Okay, so I'm gonna the overall goal of this second talk is combining the implicit neural representation with stability guaranteed interpretable non-intrusive ROM. Basically, it's linear quadratic and linear with stability guarantees to learn the evolution of parametric time-dependent PDEs. So this is our overall framework here. So we have a implicit neural representation encoder, and we're using a techniques called auto decoding to get the latent space by a inner optimization to minimize the to tune the weights, to tune the modulated variable latent state alpha, which is a linear modulation into this implicit neural representation. Okay, and then once we get this alpha for each snapshot, we have 4 snapshot here, and we get a 4 corresponding alpha. We're trying to find the alpha, trying to make sense of this evolution of alpha over time by imposing a structured, either it's stable linear dynamic system or stable linear quadratic dynamic system. Once we have that, it's a significant amount of training. Once we have that, the benefit of that is we can involve the alpha over time while we'll have the prediction continuously, continuous field prediction in the real world coordinate. Okay, so this is the how the we impose the dynamic model where the alpha is involved over time either linearly through a Koopman matrix K or through some linear quadratic operations where you have to introduce that third order tensor here. Okay, so to enforce the stability, we basically choose to we choose to using the idea of uh, from my previous postdoc group in UW promoting quadratic on promoting the Cindy stability promoting Cindy approach, and we adopted here, but in a more practical way, instead of having some of the nice formulation, we just throw everything into the loss function. So there are some interesting details that will be we'll put that in the paper. But overall, you just to make sure there's a energy conservation of the tensor Q and some eigenvalue for the linear part of the matrix. Okay, for the W1. Okay. So that's all you need. And okay, so in terms of the optimization framework that we are adopting here, so we are choosing the neural ODE framework for, but instead of having this, MLP inside of this, we are using the linear quadratic. Okay, so so now this is overall stability criterions if you're interested, but I'm going to quickly go through here because I kind of talked about before. So the incorporating the parametric effect, we are basically using the linear affine. Basically, it's a parameter affine mapping to do the to introduce the effect of parameter. Interestingly, for the Koopman case, you can actually show that if the system is parameter affine, if the nonlinear system is parameter affine, let's say 1 over Reynolds number is parameter affine to the inside the Navier-Stokes equation, and then you can actually show that if you can actually show that in the latent space of the from the Koopman operator perspective, that the effect of the parameter mu actually it should be just a parameter or still be parameter affine inside this latent space. Okay. So this is actually a homework exercise you can play around with yourself. And we also compared our ideas with some of other recent work. Okay. So what we find out is so first we test out a really simple 2D wave data set. So basically it's just a wave moving around. The wave has a constant wave speed, but it had the wave has different wave speed, and it has a Gaussian profile, and the center is kind of randomly in this 2D space. And all the boundary conditions is periodic. So we find out that if we plot in the number of parameters as x-axis and the corresponding model performance as a y-axis, we find out that our Koopman model outperforms the existing MLP models by order of magnitude in terms of parameter efficiency and accuracy. We plot these, we having those dots basically by varying the dimension of the latent states. Okay, so secondly, we tested on, beyond the, 2D wave data set, we tested on the 2D Navier-Stokes data set. And it turns out now at this time, Koopman model no longer works very well, which is expected. It turns out that stable quadratic model outperforms the MLP model a lot in terms of, if you're looking at the same loss of accuracy and you compare the number of parameter that's actually being used here. So this is over, we also actually, compared against the Fourier neural operator here. So, so here the task is, given initial state, predicting the next 19 steps. And it turns out, the stable quadratic model, as you can see here, outperforms the FNO and all the other models. Okay. So finally, we have some other tests on, flow of a cylinder here. And we split the data into training and testing, where the testing is testing on higher Reynolds numbers. And we have the, let me see, perhaps I can jump to the final figure here. Okay, so this is the final figure here for Navier-Stokes wave and cylinder flow. They are all parametric estimation problems. And it turns out under most situations, our framework, parametric stable quadratic or parametric stable Koopman outperformed the existing benchmark. Yeah. Okay, so the take-home message here is our interpretable stability guaranteed parametric Koopman or parametric stable quadratic model shows promising extrapolation performance against the existing state-of-art IRR framework. There's some disadvantage to our framework. It's relatively currently it's difficult to perform well on the high Reynolds number problems because this is a common issue in INR because we're building our framework on the on a little bit weak architecture. So in the future, we should move to the Siren, just like I have in my postdoc work. And despite the mesh agnostic flexibility and scalability to 3D, the training time for RNR is usually 20 times longer than the CNN. So currently we have developed a scalable distributed learning framework. So hopefully these can alleviate some of the problems, especially on the training on training time here. Okay. So finally, I want to acknowledge, my PhD student Sharia and Wei Chao for doing this great work. And also I want to, thank the, the fundings from the Department of Energy and RPE, and also computing resources from the RPI and NERSC. Yeah. All right. Thank you very much. I hope it's still within the time.
Yes, good. Thank you. Thank you, Dr. Pan, for the amazing talk. Yeah, I think we have a few minutes for like questions. I think if there's any audience have questions.
Hello, Professor. A really nice talk. So I have one question regarding the Koopman operator. So in the Koopman operator, typically we are supposed to expand the input state to a really, really large function space. And then the Koopman operator operates in that very large function space. However, in this cases, I see you are compressing the input state to a latent dimension or some sort of lower order representation. So is there a reason why that is Koopman?
Yes. So actually, in this example I'm showing here, none of them is compressing to a lower dimension. Actually, it's to a little bit higher dimensional oh, you're saying the Koopman work or the PDE work. So it depends on what is the original system is. So if the original system is a PDE, then you definitely have to reducing the order by compressing to a lower dimension. But if the original system is an ODE, typically we are allowed to have a little bit, higher dimension. I think it really depends on what you want and at the end of it, or maybe at the end of the days, as engineers, we care about whether it makes sense to have. We need to strike a balance between the performance and the cost. Right. So if the if ideally you should you should expand to really high dimensional space. And if you have this, if you because we don't really have for any if you give me a system, I don't really have an idea about what it is how many terms we should have in this summation for the point spectra. So what we really are doing is we're trying to find we're trying to find a reasonable amount of terms which can give us X reasonable amount of terms, giving us Y amount of performance accuracy. And if the performance and the computational cost is okay, we don't really care too much about actually we are compressing or increasing the latent dimensions. If that makes sense.
Yeah, I think it answers my question. Yeah, thanks.
Yeah. Thank you.
Any other questions from the audience? If not, I have a quick question. So about the last part about the surrogate modeling, I saw you're mentioning the like neural ODEs, I guess. How is that related to the I think you also mentioned the Koopman and the quadratic methods. So how is that related? I think I just missed some points there.
Yeah. So neural ODE, I think the most significant thing for neural ODE is it allows us to modeling the evolution of latent state using memory efficient algorithm, which is adjoint based optimization. I think that's the gist of neural ODE to SIML community. Not really having a normalizing flow model, which is in the original paper, which is the main selling point from the CS aspect. So so since you have this nonlinear, you have to model, you have to reason these latent state evolution through an ODE. What we wanted to get is a dynamic model that governs the latent state alpha. And in order to learn this governing equation for the alpha, we're using neural ODE architecture to have this, memory efficient algorithm to roll out over long times.
I see.
Yeah.
Okay. Yeah. Thank you. Yeah. And okay, if there's no more questions, we can probably end for now. Yeah. And yeah, I'll just give a closing. I thank you, Professor Pan, for the amazing talk and for the time to come here. And we'll also have seminars next week on the same time. I think it's by Dr. David Vargas. And yeah, and thank you everyone for coming. And also thanks again for Professor Pan. Yeah, I'll see you all next week then.
Awesome. Thank you, Xiyang. Thank you, everyone. Have a good weekend.